a bit of space as usual. Now, we're going to use the relatively prime theorems for theorem number 4. So before I finish cleaning this, I'll write it up. I wonder how much it would cost to have like an electronic board where I just put pressure on it and the writing came up on the board electronically, and then when I wanted to clear the error I just pressed a button and disappeared. So all you potential inventors out there, can you invent something like that for me and a zillion other professors that's cheap? That would be extremely useful, and we need it because this, frankly, this is a pain, right? It's a pain. All right, theorem 4. And it's to do with prime numbers, but it also uses okay, so you're told P divides AB. So AB are integers. And that implies, if that's true, then P divides A, or P divides B. That's almost common sense, right, if you think about it. Right? So now you've got a product, and you're told that some integer P divides it. Well, then this, either P divides the A or into the A, or P divides the B. Now, how do we actually prove it? Let's assume P does not divide A. So P divs slash, not the case. So P does not divide divide A, doesn't, right? Okay, now we're told that P does divide AB, and we're now assuming that P does not divide A. So from theorem 2, if you can remember it, so that implies, using theorem 2, if P divides the product and P does not divide the first one, so that implies that P and A are relatively prime. Okay, so P and A are relatively prime, but P does divide the product, and theorem 2 says that P must divide B. So P divides, P divides B. It divides into B. So P is a factor of B. Alright, now we can go the other way. So assume now that P does not divide into B. Okay. Now with very similar logic, so that means that P and B are relatively prime. And so again, it's just the same logic as here. So that means that so if P and B are relatively prime, but P divides the product, so P divides A. So that means that P divs A. Okay. So it's one or the other, or both. I don't know if it gets considered, but anyway. So either that's true or that's true. So P either divides B or P divides A. So that's theorem 4, done. Now theorem 5, we won't give the proof because it's rather long, but I'll just state it. Theorem 5 is the famous fundamental theorem of arithmetic. Now, we've mentioned this a bit before. I actually used it in, I think in lecture 1 on the nature of proof, in proving that there's no maximum prime number, or expressed a little differently, the number of prime numbers is infinite, just they go on forever. Now I'll state it. The actual proof is rather, well, it's fairly heavy going, and it's more in the realm of number theory than group theory. But here it is. Well, Theorem 5. Every integer can be factored uniquely into a product of primes and their powers. What does that mean? I'll give you one concrete example. In fact, I did it in the first lecture, but I'll just do it quickly again. Well, in the first lecture I chose the number 84, so let's factorize that into a product of primes. So 84 is 2 by 42, and that's 2 by 21, and that's 2 squared, and here's your power of a prime. So your product of primes and their powers. So here's a prime number 2, and to the power 2, and that's 21 is 3 by 7. We can't go any further. These are all primes now, right? 2, 3, and 7 are all primes, and we can tidy that up somewhat. So that's 2 to the power 2 times 3 to the power 1 times 7 to the power 1. Okay, so you have a product of primes to various powers, okay? And it's unique. Assuming you order the primes in increasing order, right? If you do that, then any integer can be factored down into this form of product of prime numbers with the appropriate powers. And now proving that's the case, that's non-trivial, and it's sort of out of the scope of this course, because it's a group theory course and not a number theory course, and it's non-trivial. So if you're interested, have a look at textbooks on number theory, how to prove the famous, because it is famous, fundamental theorem of arithmetic, which is Theorem 5. Theorem 6, just quickly, just mention it. Again, I won't give the proof. You can use it as an exercise if you like. Now, you're given two positive integers. In other words, A and B belong to the natural numbers. Okay, and let H is the highest common factor. Of A and B, the highest common factor. And L is the least common multiple of A and B. Now, explain what that is. Say A and B are 12 and 6. So 12 and 6. What's the highest common factor? Well, look, 2, so it's 12 and 6, okay? 2 is a common factor of 12 and 6. 3 is a common factor of 12 and 6. And 6 is a common factor of 12 and 6. So you want the highest one, so it'd be the 6. Okay? Now, a multiple, common multiple, is some number that A divides and B divides. Okay? So what would the multiple be of 3 and 7? What? Well, let's see, 3 and 7. 21. So 3 divides into 21, 7 divides into 21. Now is that the smallest one? Yeah, the least. Is that the smallest one? Well, if you had 42,